Welcome to the final video 5 of 5, Numerical Computation, and the grand finale. This is where math meets silicon, overflow, underflow, and the NN errors every practitioner dreads. Then the star of the show, gradient descent, the algorithm that trains every neural network on Earth, its 7 steps, 3 variants and failure modes. Then optimization under constraints, and a final problem where the entire unit converges. We finish with the unit summary and your exam strategy. Let's finish strong. Welcome to the third and final part, or Unit 1, Numerical Computation. Here's the theme of this chapter in one sentence. Everything so far was ideal mathematics, perfect real numbers, exact arithmetic. This chapter is what happens when that math has to run on an actual computer with finite memory and finite precision. Spoiler, interesting things break. Our root first, the floating point pitfalls, overflow and underflow, including the fix used inside every classifier. Then the emotional center of the unit, gradient descent, the algorithm that trains every neural network in existence, its 7 steps, its 3 variants and the ways it fails. Then optimization under constraints, projected gradient descent, reparameterization and the KKT conditions. And a grand finale where the entire unit converges into a single problem. This is the chapter that turns math into machinery. Let's go. Problem 1, overflow. A number becomes too large for the computer to represent. Here's the thing, a computer's numbers have a ceiling. A standard float 32 tops out around 3.4 times 10 to the 38th. Colossal, right? Now try computing e to the power 1000. That number has over 400 digits. No float can hold it. So what does the computer do? It gives up gracefully and returns infinity, or n, not a number, and n is poison. Infinity minus infinity is n times anything is n1 n in your weight matrix, and within a single training step, the entire network is corrupted. Why does deep learning risk this constantly? Because it loves exponentials, they're inside softmax and probability distributions, and because weights and activations can grow large during training. Every practitioner eventually meets the dreaded log message, LOSS, COLNO, and usually at 3 a.m. after this chapter, that message stops being panic and becomes a diagnosis. The mirror problem, underflow. A number becomes too small, so close to 0 that the computer just rounds it to 0. E to the minus 1000, an unimaginably tiny positive number. Floating point can't hold it, it becomes exactly 0. And here's why underflow is actually sneakier than overflow. Overflow announces itself infinity, n, alarms everywhere. Underflow is silent. Values quietly become 0, gradients quietly die, learning quietly stops. And log or 0, minus infinity, your probability calculations implode. No error message, just a model that mysteriously won't learn. The classic real-world case, a language model multiplying the probabilities of 100 words, each around 0.1. The product is 10 to the minus 100, underflow, 0 dead. The universal cure, and this connects straight back to our logarithm discussions, work in log space. Products of tiny numbers become sums of comfortable ones, since log of ab is log a plus log b. That's why every serious library computes log likelihoods, never raw ones. Let me show you the most famous numerical stability trick in deep learning, the one running inside every classifier you've ever used. Softmax turns raw scores into probabilities, e to the xi divided by the sum or all the e to the xjj's. It sits at the end of every classification network. Now feed it scores of 1999, 998, e to the 1000 overflow. And feed it minus 1000 instead. Everything underflows to 0 and you're dividing 0 by 0. Broken in both directions. The fix is one line and it's elegant. Subtract the maximum score from every score first. Mathematically, the answer is unchanged. Dividing top and bottom by e to the max cancels perfectly. But numerically, the biggest exponent is now e to the 01. Overflow is impossible. Watch it work. 1999, 998, subtract 1000, 0 minus 1 minus 2. Exponentials, 1.37.14. Normalize, 66, 24, 9%. Flawless from the same input that produced n. Same math on paper, radically different behavior in silicon. That's numerical computing in one slide. And now, the main event. Gradient-based learning, the idea that trains every neural network on the planet. The setup: the model's parameters, weights and biases need to be adjusted so the COST function, the error, becomes as small as possible. Gradient-based learning does this iteratively. At each step, the parameters move in the direction of the negative gradient downhill on the error surface until the error is very small. Here's the analogy that carries everything, so take a moment with it. You're a hiker on a mountain in thick fog. You want the valley floor. You can't see it, the fog hides everything, but you can feel the slope under your feet. Strategy: feel the slope, step downhill, feel again, step again. Repeat until the ground flattens. Now translate: the mountain's altitude is the cost. Your position is the parameter values. The slope under your feet is the gradient. Your stride length is the learning rate. And the fog, that's the honest part. We never see the whole landscape, only the slope where we stand. GPT was trained by this exact idea, just with billions of coordinates instead or two. Next, the recipe, step by step. The gradient descent recipe: steps 1 and 2, define the goal and measure the error. Step 1: the goal, minimize the cost function, which measures the gap between the actual output y, the ground truth, and the model's prediction y hat. Step 2: compute it. The cost j of theta is the average of the per example losses over all m training examples. Theta stands for the parameters, the weights we're tuning. Now, a distinction the textbook flags as important and examiners quietly adore. Loss function: the error of one single example. COST function: the average error across all training examples. Loss is one house's mispricing, cost is the whole dataset's report card, and one reframing that unlocks everything. J is a function of the parameters. The data is fixed, frozen. What varies is theta. So imagine a landscape where every location is a possible setting or the weights, and the altitude is the cost there. Training means finding the lowest point of that landscape. Hold that image. The next slide takes our first step down. Steps 3 and 4, the mathematical heart of deep learning. Find the slope, step downhill. Step 3, compute the gradient, the partial derivative of the cost with respect to each parameter. The gradient answers one question: in which direction does the cost increase fastest? Step 4, move the opposite way. The update rule: and if you memorize one formula from this unit, THIS is it, theta becomes theta minus alpha times the gradient. Let's decode the sign because it trips everyone at least once. The gradient points uphill. We want DOWN, so we subtract. Concrete numbers: theta is 4, the gradient is plus 6, uphill is to the right, alpha is 0.1. New theta 4 minus 0.6, 3.4. We stepped left. Downhill? Correct. Alpha, the learning rate, is a small positive number controlling the stride. And that's it. That one line, repeated millions of times, is how every neural network learns. Backpropagation: next unit star is merely the clever bookkeeping that computes these gradients fast. The learning itself, you just saw all of it. Steps 5, 6, and 7: tuning, looping, and knowing when to stop. Step 5, respect the learning rate. Too high and you overshoot the minimum, bouncing across the valley, possibly diverging entirely. Too low and training takes forever, burning computation. The right alpha gives fast yet stable convergence. We'll dwell on this on the next slide, it deserves it. Step 6, iterate. Repeat the compute gradient, take step cycle. Stop when any of 3 conditions hits, the cost change becomes negligible, you reach the maximum number of iterations, or the cost approaches 0. Those 3 stopping criteria make a tidy exam list, by the way. Step 7, terminate. Cost minimized, parameters stable, the model is trained. One vocabulary note to bank: one full pass through the training dataset is called an epoch. When someone says they trained for 50 epochs, the model saw the entire dataset 50 times. You'll hear that word in every deep learning conversation for the rest of your career. The learning rate deserves its own slide because it is by universal agreement the single, most important hyperparameter in deep learning. And the story is pure Goldilocks. Alpha too high, your steps overshoot the valley and bounce wall to wall. The loss oscillates wildly or explodes into NON. Sound familiar? This is one of the roads to that 3 AM error from earlier. Alpha to LOW, microscopic baby steps. Convergence takes geological time. The loss curve is a flat, sad line and your GPU bill grows, alpha just right, a smooth, steady descent to the minimum. Now the practical skill diagnosis from the loss curve. Loss exploding or zigzagging, lower the rate. Loss flatlining, barely moving, raise it, or train longer. Isvan Glanslav's half the My Model Won't Learn posts on every forum. How do professionals choose? They sweep on a LOG scale trying 0.1, 0.01, 0.001, never, in tiny linear steps. Adopt that habit early, it's the pro move. Here's a question that sounds trivial but defines the whole training experience when computing the gradient. How much data should we use per update? 3 answers exist and they are either 3 variance or gradient descent. Same update rule, the only difference is the serving size. Batch gradient descent, use the entire dataset for one update. One update per epoch. Stochastic gradient descent SGD, update after every SINGLE sample. Thousands of updates per epoch. And mini batch, the compromise small groups, typically 50 to 256 samples per update. The trade-off in one line: batch is stable but slow, stochastic is fast but noisy. Mini batch buys most of both benefits, which is why it's the default in modern deep learning. And a connection to smile at. One mini batch is processed as one matrix multiplication, the operation from our linear algebra chapter that GP us devour. The chapters are holding hands again. Let's examine each variant properly. Variant 1: batch gradient descent, also called vanilla gradient descent, the original recipe. The mechanics: compute the error for every sample in the dataset, but update the parameters only once after the entire dataset is processed. One epoch, one update. The advantages: with the whole dataset consulted, the gradient is exact, updates are stable and smooth, convergence is calm and predictable. It also parallelizes nicely on modern hardware. Now the disadvantages: and at modern scale, they bite hard. It can settle early into a merely okay solution. It needs the whole dataset in memory, and it's slow. With 10 million images, you compute 10 million forward passes for one parameter update. Want just 10 updates? 100 million passes. The verdict: perfectly fine for small classical datasets, rarely used in pure form for deep learning. But it sets up the trade-off perfectly, because the next variant flips every one of these properties on its head. Variant 2: stochastic gradient descent SGD, the polar opposite or batch, update after every single training sample. See one example: adjust immediately, repeat. Thousands of updates per epoch, with the error path jumping up and down noisily instead of descending smoothly. The advantages: immediate progress, easy to implement, quick learning at the start, minimal memory, one sample at a time, and it handles huge datasets well. But here's the profound part, the point I most want you to remember: that noise is secretly a feature. Remember local minima, those small dips that trap smooth descent. SGDSS random jolts can kick the search right out of a bad valley, like shaking a jar of mixed nuts to help everything settle properly. Batch gradient descent in its perfect smoothness stays trapped. Imperfection as a virtue. The honest costs per sample updates are computationally heavy at scale, and near the end of training, the same beloved noise prevents settling precisely at the minimum. Fast and jittery versus slow and smooth. Surely there's a middle path. Next slide. Variant 3, mini batch gradient descent, the Goldilocks solution and the undisputed champion of modern deep learning. The recipe: split the training data into small mini batches, typically between 50 and 256 samples, and update after each one. Why it wins on both fronts: updates come far more often than batch, so learning is fast and bad local minima get escaped. Yet each update averages over enough samples that the worst noise cancels out. More efficient than SGD, lighter on memory than batch. And the hardware bonus we keep meeting: one mini batch equals one GPU-friendly matrix multiplication. The batch size is literally chosen to fill the GPU's appetite. That's why you'll see powers of 230, 264, 128. The costs are mild: one extra hyperparameter to choose the batch size, and error still accumulates per batch before each update. Here's your decoder ring for every tutorial you'll ever read. When the code says data loader, batch size equals 64, that is mini batch gradient descent. You now know exactly what that line means. The three variants side by side, one table to rule the whole comparison. Update frequency: batch once per epoch, stochastic every single sample, mini batch every 50 to 256 samples, gradient quality: batch exact and smooth, stochastic very noisy, jumpy path, mini batch mildly noisy, mostly smooth. Memory: batch needs the entire dataset at once, stochastic just one sample, mini batch one small batch. Speed at scale: batch is slow, updates are rare. Stochastic starts fast but struggles to settle. Mini batch fast and stable. And the verdict: row: batch for small datasets, stochastic for streaming data, mini batch the deep learning default, with the star to prove it. When the exam says compare the three types of gradient descent and some version of that question is nearly guaranteed this table is the full mark answer. It's worth a photograph. So far we've pictured the cost surface as one friendly valley. Time for the uncomfortable truth. The convex problem is bowl-shaped, one valley, one minimum, and gradient descent finds it, guaranteed every time. Linear regression lives in this paradise. Deep learning does not. Neural network cost surfaces are non-convex, a vast mountain range or ridges, valleys and plateaus. Two traps await. Trap 1, the LOCAL minimum. A dip that's the lowest point nearby but not the true bottom. The gradient there is zero, descent stops, satisfied while a better value waits beyond the ridge. Picture a golf ball resting in a small divot while the actual hole sits 50 meters away. Trap 2, subtler, the saddle point. Slope 0 but not a minimum, shaped like a horse's saddle, downhill ahead, uphill to the sides. Surprising fact from high-dimensional geometry: with millions of parameters, saddle points vastly outnumber local minima. To be a true minimum, you must curve upward in every 1 or million directions at once. And the practical medicine: you already know it, SGDSS noise, the random kick that pops the golf ball out of the divot. Two more failure modes, and these are the deep learning coming back to bite. Vanishing and exploding gradients. The mechanism first, because it explains both. Backpropagation multiplies many layer derivatives together, chain through the depth or the network. Now multiply 50 numbers, each slightly less than 1. 0.9 to the 50th is about 0.5%. Practically nothing. Multiply 50 numbers slightly more than 1. 1.1 to the 50th is over 100. Explosion. Vanishing gradients, the signal shrinks to nothing on its way back. The early layers barely update, learn glacially, or stop entirely. Exploding gradients, the signal balloons, weights blow up, training destabilizes, and sometimes weights become NN. There's our 3 AM friend, one more time. The fixes, as an exam-ready list: gradient clipping, cap the gradient's size, better weight initialization, ReLU activations instead of sigmoid and tan, and dimensionality reduction, especially common in recurrent networks. A story Unit 5 will tell properly. New scenario: what if you must minimize a function but you're not allowed to go just anywhere? Welcome to constrained optimization. Formally minimize f of x, subject to x belonging to a set S. The feasible set points inside S are feasible points, everywhere else is off limits. Constraints come in two flavors: equality constraints g of x equals 0 and inequality constraints h of x at most 0. A small convention to note: budget at most 5,000 becomes spending minus 5,000 at most 0. Everyday version: minimize travel time, subject to cost within budget. Machine learning version, and here's where it gets relevant: minimize training loss, subject to the norm of the weights staying at most 1. Why cap the weights? Because remember the norms chapter, small weights mean simpler, smoother models that generalize better. Sound familiar? This is regularization, wearing formal clothes. The norm ball constraint controls model complexity and prevents overfitting. The next 3 slides give 3 different ways to actually solve such problems. Method 1 for constrained problems, and it's beautifully blunt: projected gradient descent. PGD. The recipe has 3 steps. Step 1: take a normal gradient descent. Step: pretend the constraint doesn't exist. Step 2: check did we land inside the feasible set. If yes, carry on. Step 3: if no, project back, snap to the closest point inside the feasible region. The mental picture: a dog on a leash. The dog lunges wherever the scent the gradient leads. Whenever it strays past the leash's length, it gets snapped back to the boundary. Descend project, descend project. For the norm ball constraint, the projection is one line. If the vector is too long, rescale it back to length 1. Practically free. And a spicy real-world footnote. PGD is the standard tool for crafting adversarial examples, those invisible image perturbations that fool classifiers where the perturbation must stay imperceptibly small, an L-infinity constraint. Our worst-case norm from the linear algebra chapter, now starring in AI security research. Method 2 and is1 solves constraints with pure elegance, the reparameterization method. The exam-ready definition: reparameterization converts a constrained optimization problem into an unconstrained one by expressing the constrained variable through new free parameters. The philosophy shift is the beautiful part. PGD enforces the constraint, it polices violations after each step. Reparameterization makes violation impossible by design. Like train tracks, instead of policing a car to stay on the road, build the vehicle so it physically cannot leave the rails. Then drive as fast as you like. The classic example: require the vector x to have norm exactly 1 in 2 dimensions. Write x as cosine theta, sine theta. Check the constraint: cosine squared plus sine squared equals 1. Always, for every theta, violation is mathematically impossible. So minimize freely over theta, no constraints, no projections, gradient descent runs blissfully unaware. Modern footnote for the curious: variational autoencoders are trained by a famous reparameterization trick, the same idea at the frontier. Method 3 is the theory, the mathematical certificate behind all constrained optimization, the Karush-Kuhn-Tucker conditions. KKT. KKT provides the necessary conditions for a solution to be optimal when both equality and inequality constraints are present. It generalizes the classical Lagrange multiplier method to handle inequalities. The construction: for every constraint, introduce a multiplier lambda for equalities, alpha, required non-negative, for inequalities. Then build the generalized Lagrangian, the objective, plus each multiplier times its constraint. One function now carries the whole problem, objective and rules together, converting constrained into unconstrained. And here's the interpretation that makes multipliers feel real: each alpha is a PRIC. Economists call it the shadow price, how much the optimal value would improve if you relax that constraint by 1 unit. A constraint that doesn't bind costs nothing. That thought becomes a theorem on the next slide. Historical loop worth savoring: support vector machines, the algorithm that once eclipsed neural networks in our history chapter, are trained by solving exactly a KKT system. The KKT picture completes with one crisp distinction: at the optimum, every inequality constraint is either active or inactive. Active, h equals 0 exactly, the solution is pressed right against the boundary. This constraint is genuinely shaping the answer. Inactive, h strictly below 0, the solution rests comfortably in the interior. The constraint might as well not exist, and its multiplier is exactly 0. The room and walls analogy makes it obvious. If the best spot is the middle of the room, no wall matters, all inactive, all alpha's 0. If you're pressed against a wall, that wall is active. It's physically holding the solution in place, and its alpha measures the push. Those two cases compress into one elegant equation: complementary slackness, alpha times h equals 0 for every constraint. Either the multiplier is 0 or the constraint is tight. A wall you're not touching exerts no force. And the SVM loop closes perfectly. The support vectors that name the algorithm are exactly its active constraints, the data points pressed against the margin. Beautiful. The final topic, and I've saved it deliberately, because linear least squares is where our whole unit converges into a single problem. The problem: find x minimizing 1/2 the squared L2 norm of ax minus b. In words, make ax as close to b as possible when an exact solution may not exist, fitting the best straight line through scattered points. Is this problem, the squares being minimized are the squared vertical gaps. Root 1 calculus: set the gradient to 0 and outfall the normal equations. A transpose ax equals a transpose b, solvable with an inverse. Root 2 iteration: run gradient descent with this gradient. The practical choice for huge systems. Root 3, the pseudo-inverse, built from SVD, handles even the degenerate cases. Now watch the convergence. The L2 NORM defines the objective, transpose and inverse solve it exactly, SVD rescues the singular case, gradient descent scales it up, and under Gaussian noise its maximum likelihood. The probability chapter taking a bow, every chapter of this Unit 1 problem. That's not a coincidence. That's the design of the subject. The final quiz, and it's a practical one. This is the question you'll face in real life, probably at an inconvenient hour. During training, your loss suddenly becomes n after a few epochs. Based on this unit, which is the most likely combination of cause and fix. Option A, underflow of probabilities increase the learning rate. Option B, exploding gradients causing overflow lower the learning rate, or apply gradient clipping. Option C, a saddle point stop training, the model is done. Option D, vanishing gradients remove all hidden layers. Think like a doctor, match the symptom to the disease. What does NN specifically tell you? Which failure mode announces itself that way? Pause the video and make the diagnosis. The diagnosis: B, exploding gradients causing overflow, treated by lowering the learning rate or clipping gradients. Here's the pathology. Exploding gradients make weights enormous, exponentials of enormous numbers overflow to infinity. Infinity minus infinity yields NaN, and NaN poisons everything it touches. The standard first aid: smaller steps, a lower learning rate, or capping the gradient's size with clipping, plus the stable softmax trick running as a vaccine. Now why the others fail? The differential diagnosis. Underflow gives silent zeros and a stuck loss, never NaN, and raising the learning rate would pour fuel on any instability. A saddle point gives a plateau, a flat, boring loss, not corruption, and vanishing gradients cause frozen early layers and slow learning, while removing all hidden layers would simply destroy the model. Each failure mode has a distinct fingerprint. NaN means explosion, flatline means vanishing or a plateau, silence means underflow. Learn the fingerprints and you can debug half of deep learning by symptom alone. That skill might be the most practical thing in this whole unit. And here we are, the summit. Let's look back at the entire territory we've covered in 10 takeaways. Try to explain each to yourself before I do. Deep learning: multi-layer networks that learn features automatically. The 3 learning types: supervised with labels, unsupervised for patterns, reinforcement from rewards. Data is tensors, scalar to vector to matrix and beyond, with shapes that must always match. Norms: L1 the taxi, L2 the crow, L infinity the worst case. Eigen and SVD, a V equals lambda V, and any matrix is rotate, stretched, rotate. PCA: standardize, covariance, eigensolve, project. Probability distributions: binomial and Poisson, the 3 flavors: marginal, conditional, joint. Bayes rule: posterior equals likelihood times prior over evidence, and never forget the 17%. Gradient descent: theta minus alpha times gradient batch, stochastic mini batch. And constraints: project back, reparameterize, or certify with KKT. If you can explain all 10 in your own words, you haven't just covered Unit 1. You own it? Let's talk strategy, how this unit actually shows up in exams. 5 question archetypes, and you've seen them all. Archetype 1: define and exemplify. Scalar, tensor, random variable, sample space. 1 crisp definition plus 1 example each. The examples on our slides are exactly the currency you need to compute. Norms of a small vector, eigenvals of a 2 by 2, a binomial probability, a covariance from a 5-row table, a Bayes posterior. Every one of these appeared as a worked example in this series. Redo them whole. 3. Compare. Classification versus regression. The 3 gradient descent variants. Marginal versus conditional versus joint. Our comparison tables are those answers. 4. Explain the steps. PC has 4 steps, gradient descents 7, PGDSS 3. 5. Diagnose. Overflow versus underflow, vanishing versus exploding, learning rate pathologies. The golden strategy: every quiz in this series plus every worked example is a past paper question in disguise. Master those and you walk in prepared. Before we close, where to go next, because this unit is a beginning, not an end. The primary text: Deep Learning by Goodfellow, Bengio and Corville, and here's the wonderful part, it's completely free, legally, at deeplearningbook.org. This unit was chapters 2, 3 and 4. for visual intuition, and I cannot recommend this strongly enough. 3 Blue 1 Brown's Essence of Linear Algebra series on YouTube. His eigenvector animations achieve in minutes what pages or text cannot. For practice, Khan Academy's probability courses and MIT's OpenCourseWare linear algebra lectures by the legendary Gilbert Strang. But here's my strongest advice: implement things. PCA's about 10 lines on NumPy, gradient descent 5. The moment you watch your code descend a loss curve, this stops being theory forever. A good weekly rhythm: 1 video for intuition, 1 worked example by hand, 1 small notebook implementation. Intuition, pen, code. That triangle is how this subject becomes yours. And that is Unit 1. Complete? Take a second to appreciate the distance you've covered. You started with a single number, a humble scalar, and you ended debugging n losses in neural network training. Along the way, the language or linear algebra, the logic of probability, and the machinery of numerical computation. The 3 pillars standing. My parting requests: revisit the 5 quizzes in a week. Spaced repetition is unreasonably effective. Redo the worked examples with a pen. The hand remembers what the eyes forget. And visit deeplearningbook.org. In the next unit, everything we built here comes alive: machine learning fundamentals in depth, and then at last real neural networks, trained end-to-end with backpropagation. Thank you for learning with me. Keep your curiosity sharp, and I'll see you in Unit 2. If this lecture helped you, do like, share, and subscribe to Shri Tech Bytes for more lectures like this one. See you in the next video.